Hello everyone. In this screencast, we're going to look at using Dask to scale Python analytics workloads on high-performance supercomputers. So Dask is a library for parallel computing, integrates with other Python libraries like NumPy, Pandas, or scikit-learn. It works well on traditional data science environments like a Hadoop cluster or a cloud cluster, but also works very well on high-performance computers, the kinds of things that might run job schedules like PBS, SGE, Slurm, or something else. Today we're looking at the Cheyenne supercomputer. This is a classic supercomputer run by UCAR. Does a lot of atmospheric science work. And today we're going through a few different things. We're going to be installing a local Python environment with Miniconda. We're going to be using the dask-jobqueue subpackage to create a Dask cluster using our supercomputer with some simple computation just with IPython. Then we'll look at building a configuration file, something a little more robust that we can share with a larger group. We'll look at doing some SSH tunneling to get at the Dask dashboard. Then finally, we'll use JupyterLab on the supercomputer and SSH tunnel to get that from our laptop. This will give us a nice interactive workflow on the supercomputer using Jupyter notebooks and Dask. Hopefully, this will all provide a nice picture and take someone from no experience with Dask or running Jupyter on a supercomputer to being able to use that supercomputer as they would use their laptop, just much, much bigger. Okay, so let's get started. Our first step will be to install Miniconda. So I have SSH'd into Cheyenne here, my supercomputer. I'm just on a login node. You can see it's called Cheyenne 1. And I'm going to install Miniconda. I don't have to do this, so if you look at which Python I'm using, this is the system Python. This is administered by IT, and if I try to install something into this version, they might not like that, or I might not have permissions to do so. You can install things into user space with pip. That gets a little bit confusing sometimes. I personally prefer to use Miniconda. It creates an isolated environment in my local machine. So I've gone here to conda.io/miniconda.html. You can also install all of Anaconda. That's just a little bit smaller. I'm going to copy this address and just download it here. There, I've downloaded Miniconda. I now need to run it. And we should read these terms. I accept these terms, and I'm going to place it somewhere. I'm going to place it into just the Miniconda directory, but you can place it wherever you like. I'm going to pause the screen recording just so this runs a little bit faster. Yes, I do want to add that, and great. So I'm going to now, I have to log out and log back in order for Miniconda to have taken effect. Great, so now if I type in which Python, we see this now pointing to a Python that's within my home directory. So I have full control over this environment. I can do anything I want to it. First thing I'm going to do is I'm going to conda install Dask and IPython. I'm going to install Dask for parallel computing, and IPython for just some small interaction. That will also take a second as it's installing packages. Great. That may have taken about a minute or two to run. And now, if we type in IPython, we should have a nice interactive prompt locally. We should be able to import libraries like Dask and dask.distributed. Great. So we're also going to need one more library to interact with a high-performance computing system. We library dask-jobqueue. You can pip install this, or you can conda install it on CondaForge. I'm just going to pip install it for now. And the dask-jobqueue package, let's go and look at the documentation. The dask-jobqueue package will provide some nice capabilities for us to easily interact with common job schedulers like PBS, Slurm, SGE, or Moab. If you have some other job scheduler, it's probably also easy to support. So let's go ahead and look at that next. So now I'm going to start up IPython and import the dask-jobqueue library. I want to import, let's see what options I have here. I'm going to type here and then press Tab. You see the options that we have. We'll look at the PBS cluster. So we can use IPython to show us the options for that object with a question mark. And some of these options are specific to the job scheduler, like the queue in the project that we're going to use, and some of them more specific to Dask, like the number of cores in memory per job. So that's using the question mark operator. Go ahead and make a cluster. Make a cluster with, so I'm now going to provide some information about the jobs of my eventual cluster. So this most likely is going to represent the number of cores in memory we're going to have on a single node in the cluster. Here each node has 36 cores and I believe around 100 gigabytes of memory. Notice this isn't the amount that I want total, this is per job or per machine that I'm going to use. I'm also going to add some information here about the PBS queue, or the queue I'm going to be submitting to. This is often arguments like regular or priority or debug, and the project that I'm going to be using. This is specific to me and my group. This is probably something that you provide whenever you submit a job. If you don't know these things, you should ask IT, it'll have the right values for you. So that hasn't done anything yet. That is, provided a specification that we're going to use to submit jobs. Let's go ahead and ask for 10 workers, each with these specifications. So let's go ahead and look at, I'm going to log into Cheyenne again here, just so I can get another terminal up. I'm going to use qstat and look at all the jobs that I've submitted. And so we can see that I have submitted 10 jobs, and they're all in the running state. So we're up and running already. So let's do from dask.distributed, import client. This is how Dask is going to connect to that cluster we've created. And we're going to create a client object and give it the cluster that we just created. So this client says that yes, I see that there are 10 processes and 360 cores. Great, it can now do things with that. Now just to be clear, if I were to scale up larger, say I'm going to ask now for 20 machines, I can do that dynamically and that's nice. Look at the client, it may not see those machines immediately. It may take a while for them to get through the queue. So it looks like they did all now start, and now in a second or two, now I have even more computation. But if you're not seeing anything come through, if you've asked for more workers and they haven't happened yet, it may be that you should check out the queue of your job manager and see if they're finished or not. Okay. Now let's just do a simple computation just to sort of show that we can parallelize out. We're going to, let's see, import time. Let's make a function maybe slow increment that takes in a number and returns, maybe it's going to sleep for maybe a second, and then return that number plus 1, just to simulate some work. Let's import also dask.distributed, import progress, for we get some nice progress bars. Let's make a bunch of futures. So there are many different ways of using Dask. You can use it with arrays, you can use it with data frames, you can also use just normal Python functions like how we're doing now. And so let's just call that Python function many times, maybe on maybe 1,000 inputs, and we'll look at how that progresses over time. So let's do something bigger. Let's do, we've got 720 cores here, let's go for 5,000. So that's submitted 5,000 tasks, each of which are taking a second, and we're able to churn through all of those in around 7 seconds. That's because we have access here to 720 cores on our cluster. So this shows that we can use the PBS cluster object to define a specification for a job. Then we can ask for a number of workers that meet that specification. We can change that over time. We can connect to that cluster with dask distributed, and we can execute some work. Just to show briefly what's happening under the hood, we can look at the cluster.job script function. Let's print the result of that. So if you're familiar with running jobs with job scripts, this might look familiar to you. All dask-jobqueue did is it took our arguments from above and it constructed a small job script which told PBS how to launch a single Dask worker with the parameters that we provided. So all dask-jobqueue is doing when we press scale is it's just submitting this job many times. Those are connecting back to our local machine and giving us some more computation that we can work with. Okay, so it's a simple way of setting up Dask using IPython and dask-jobqueue on a PBS cluster, or really most other kinds of high-performance machines. So next we're going to look at configuration. So if we scroll up a little bit here to the top, we recall that we had to, when we created our PBS cluster, we would provide a lot of information telling PBS or dask-jobqueue how to configure our machines. And this is a little bit error prone, especially going to new users. So we'll look at how to record all this information into a config file that you can then use to make this more automatic, which is especially useful when scaling this out to a team of people or to new people. So we're going to leave this IPython session for a moment. And we're going to look at, so when dask-jobqueue was first imported, it created a file in my home directory, in the .config directory. And if you look at what's there, there should be a few libraries that are, for example, matplotlib. Looks like it also has a config there. We'll look at Dask, and this has a few different configuration files as well. We're going to look at the jobqueue file. So by default, all of this is commented out, and there's a different configuration setting for each of the various schedulers. We only care about PBS here, although you may care about one of these other ones. So I'm going to remove the others just for now. We don't need these. I'm going to uncomment these. Okay. So these are the defaults that dask-jobqueue has, and we can now fill these in with what we'd like them to be instead. So instead of null cores, we might ask for 36 cores. Whoops. Because I happen to know that's the size of my machines. And memory, we want 100 gigabytes. Interface is the network interface that I want to use for my workers. I happen to know that my interface is IB0. So there's probably a few different interfaces. You might check with ifconfig if it's available on your machine. And there's a variety of different network interfaces available on your machine. Things like ETH are quite common for Ethernet on more commodity hardware. This is probably going to be the default that Dask will use because it won't know what to choose. But IB0 here is InfiniBand, and that's going to be a little bit faster. So we're going to choose that. That's optional, you don't have to do that. If it doesn't work, don't worry about it that much, but it's a nice thing to do. Local directory, this is where Dask should store data if it happens to need to spill the disk. This is often something like local storage if you happen to have it. Maybe your nodes have maybe some SSD on them, and you might provide a path here. Maybe it's something like /scratch or /temp or something like that. You can also have Dask never ever write to disk. This is a common request for high-performance computer systems. And we'll see how to do that in a little while. Moving on though, the queue I want to use by default is regular. And my project again was UCLB0022. I tend to prefer a short wall time by default for my workers. I tend to create workers, use them for a little bit of time, then destroy them. And having a short wall time gets me into the queue more quickly. If I ask for 10 hours, it's going to take a long time for PBS to find a slot where I can put that job. So sort of a trade-off here between when do you want your jobs to die and how quickly you want to get into the cluster. I tend to prefer many short, fast jobs, and it's okay if they die. Dask can recreate new ones. And so it's you could have many jobs be created and die over the same session. None of these other things I really care about, but if you have particularly fancy requirements on your cluster, you may want to add some things here, but we'll remove them for now. So great, I provide all the configurational options that I care about. Now if I go back to IPython, I import dask-jobqueue again. When I make my cluster this time, I can just make it with no arguments. This is a lot simpler, both for me, because I type this very frequently, and because I might give my configuration file to someone else on my team, and that stops them from having to think about it that much. That being said, I can still, if I want to, I can overwrite those options. I might say queue equals priority for this job, for example. Or maybe I know that I'm going to be building to a different project. My colleague gives me some other building code. I can use that instead. So that's a fine way of doing things. Okay. But let's go back again to our configuration files. And let's look at also the distributed configuration file. We mentioned before that we want to avoid writing to disk unnecessarily. There's also an option that's mentioned a lot in the Dask documentation. So if you go to deploy and then high performance computers, there's a lot of information here about various suggestions on how to do high performance computing well. One of them is no local storage, which is a common situation. And here's a bit of configuration that we can use. We can add this to our config file. Looks like Vim might accidentally splay that out. We can copy and paste this into our configuration file, and Dask defaults will now not spill the disk by default. There's many other configuration options. If we look at .config, Dask, and then distributed, we can see that we stole this configuration from the distributed file. And there's many things that you could tweak here if you wanted to. Here they're in separate files. We've got the jobqueue.yaml file and the distributed.yaml file, but it doesn't really matter. They can live in any file. So now I have this nice configuration file. It defines my cluster. It also stops me from writing to disk, which again is useful in some systems that don't have local storage. And I can now share this with any colleague. If I run a cluster, I could also copy this into the /etc/dask directory. If you happen to be a system administrator, you might want to do this just to help any other Dask user on your cluster not have to worry with any of these options. Now, not all of these are appropriate for all users. You might want to remove some of these, for example, but the others are very likely to be system-wide. But if you're not a system administrator, you might just share these with your colleagues and ask them to put it in the .config/dask directory of their home directory. For our next step, we're going to use SSH port forwarding to give us access to the Dask dashboard from a local machine. So stepping back a moment, Dask runs a nice dashboard that helps users understand what's happening in the cluster as they're running computations. That dashboard is like a normal HTTP server running on the supercomputer. We'd like to get access to the dashboard from our local machine, maybe our laptop that we're sitting with, in a browser like Chrome or Firefox, but it's hard to get that web browser to talk to our local machine. SSH port forwarding has helped solve that problem. We're also going to use this later to get access to Jupyter, so it's going to be useful in two different ways. So I'm going to, from my local machine, so notice here this is my local workstation, and this here is a terminal on Cheyenne. I'm going to SSH with some new commands. -n, I don't want to run a command. -l, I want to forward a port. I'll forward the port 8787, which is the default Dask dashboard port. I'm going to give it the host name of where I'm running my Dask commands. Here I'm just running it from the login node. I also want to forward the port. Later on, we're going to use this 8888, which is the default port for Jupyter. We're going to point those to our local machines. If you are running a server on your local machine with either 8888 or 8787, you might want to close that beforehand. And then we're also going to give my login at the publicly accessible address of my cluster. This is the address I use when I first SSH into machines, not necessarily the machine I'm on right now. So I have to log in. Great, now I'm forwarding ports. So let's go ahead and let's see what that looks like for a moment. So again, on the right here, I'm on the supercomputer. Let's create a PBS cluster again. So that's now running a dashboard on the supercomputer, but due to port forwarding, I can go to localhost 8787, the default port, and /status, which is the default page. And so it looks like I'm running this thing locally, but actually this is being hosted from the high-performance computing system. So let's scale that up. We're going to ask for 10 workers. Let's go to the workers page of the dashboard to see what's around. At first we have no workers, but over time, as those jobs start making it through the queue, we'll start seeing them. So let's go ahead and we'll look at using exclamation mark and IPython to run a normal bash command. Look at the status of the queue. We see that they're all indeed in the queuing state. They're waiting to be let through the job queue. Oh, looks like 2 of them have arrived. So we can see that using the dashboard can give us some more nice information about our cluster rather than having to rely on, say, these bash commands. While the other jobs are coming in, let's set up a nice computation with dask-array. So let's first, as before, import client from dask-distributed and give it access to our cluster. Now let's import, last time we used the map method on the client object. Now instead we'll use dask-array, which will give us, import dask-array as DA, which will give us a nice NumPy-like interface. So let's go back to status. So let's create a random array. This will be small. And let's ask Dask to persist that into memory. If you want to learn more about how to use Dask, I recommend going to the documentation. There's many different APIs. I'm showing you a couple ones here, but that's not the point of this screencast. So we can ask Dask to persist that in RAM, and now we have a few hundred tiny small NumPy arrays on our cluster. Let's do something a little bit bigger. So let's increase that by, let's say, a factor of 5 in each, a factor of 2 over here. That should be just fine. So now we're sorting 20 gigabytes of RAM, 20 gigabytes of data on our cluster. That's actually a very small fraction of our total cluster size, but we can just go ahead and do some simple things. So this is adding x to its transpose, uses a lot of communication, a lot of read, and then subtracting off the mean. So again, we're using our cluster interactively, and we can do things like y.sum. And what's nice is that we get to see, with this nice dashboard, all the things that are happening on our cluster, even though we're on our local laptop. There's a lot of other information here if you want to go investigate things. We can go see the full task graph of the computation we just did. See that it's fun and interesting to watch. So again, we're using SSH tunneling to get access to a web server running on our remote machine locally onto our local machine. So this is a very nice environment. We can now run with IPython on the right, and we can get nice distributed computing, and we can see what happens in distributed computing on the left. We're going to use the same trick we used to get the dashboard to also get access to a Jupyter notebook system. This is going to be useful for a few different reasons. So I'm going to leave this IPython session, and I'm going to install JupyterLab. So Jupyter notebooks have been very popular for a long time. JupyterLab is like Jupyter notebooks. It includes them, but also includes some other things like terminals or a file browser, which are nice to have in a remote system. This is going to take a couple seconds, or more like a minute, to fully install everything, so I'm going to pause. So now we could type in JupyterLab like normal. There's a few other things we're going to do now to be a little more careful. First, we don't want this local machine to start up a browser because it can't. We're not running Chrome on our supercomputer. So we're going to type in the no browser flag. Secondly, we're going to want to add a password, and we're going to want to put a little bit with host names. So if we ran that, it would tell us go ahead and click on that link and you'll be taken to Jupyter. That's not true because of the port forwarding. A couple of things will have to change. So we're going to cancel that by hitting Control-C a couple of times. We're going to do two things. First, we're going to create a configuration file using the generate config command. Then, so that will store that file in our home directory, in the Jupyter directory, and in the Jupyter Notebook config file. In this, we're then going to go look for the password entry. And we're looking for, here, the C notebook app.password entry. So what we can do, so it provides instructions here on how to generate a password. We're not going to write our password in here like password. That's not what we're going to do. Instead, we're going to hash our password by running this code. So I'm going to poorly choose the term password here. I'm going to type it in twice. And here's the SHA for that. I'm going to include that hash here. I want to make sure that it's all on one line, and also that I've uncommented that line. Great. Now my Jupyter Notebook server is nicely protected. So I'm going to type again JupyterLab, no browser. I'm also going to give it a new IP. I'm going to give it the hostname IP. So I don't want it to think that it's called localhost. It's actually going to be called Cheyenne5 when I connect to it. So let's run it like that. And now, when I go over here to my browser on my local machine, I've got a localhost, 8888. That's the default port for Jupyter. It's also the port, recall, that we are port forwarding. And now when I log in, I'm getting this nice password page and enter my nice password there. So this gives me a nice JupyterLab environment, which is useful for a few reasons. Like with the classic notebook, I have access to notebooks, but I also have access to things like terminals or text editors or file browsers. For example, I look at my files, and I can navigate into these directories. I can look at them. I might, for example, pull up the license of Miniconda and look around and play with it. So I have now access to a more visual or more easy to use user environment. It's not for everybody, but some people would really prefer this. Similarly, I can looking at commands. I can look at a new terminal, and I can launch many new terminals from inside this JupyterLab environment, and they're just normal Linux, Unix terminals. But we came here first to play with dask-jobqueue, so let's do that. So let's make a new notebook. Let's get rid of this. From dask-jobqueue, import PBS cluster. Cluster equals PBS cluster. I regret now not also installing the IPyWidgets package. If we had done so, this cluster would have a nice object that would have buttons allowing us to scale it and such. But we'll just be a little low-tech for today. Cluster.scale, let's ask for 10 machines. So let's move this over to the right. I find it's very helpful to have Jupyter on one side of my screen and the Dask dashboard on the other. That way, I can play around on the right and see what's happening on the left. So from dask.distributed, import client, client equals client, cluster. Hopefully this is familiar by now. And we can do things like, let's say, let's import Dask data frame as d if you'll do. Let's make a simple time series data set, and let's persist that into memory. So again, I'm now operating with the Jupyter Notebook on the right. I've got distributed computation on the left. I can scale things nicely up and down as I like. This is a very nice sort of interactive work environment, very similar to what I normally do on my laptop, but now, if I want to, I can scale out not to 10 machines, but I can scale out to 100 machines. So I can really scale this interactive workflow nicely across a large supercomputer that I have access to. So this moves what was previously more of a batch-oriented system, a high-performance supercomputer, designed to run MPI jobs, and turns it into a fully fledged interactive data science environment. So that's all. Thank you all for your time. Some things to look at in the future. You might look at the dask-jobqueue documentation. This goes through some of the things we mentioned before. You might also look at the Dask documentation and the high-performance computing section within Setup. So within Setup, there's high-performance computers. There's a variety of configuration things you might want to look at. We also played with configuration. Take a look at configuration here. And there's a variety of ways in which you can specify configuration in Dask. This is more useful if you want to share your configuration with teams or ways to help maybe system administrators help design clusters, default Dask configurations for clusters. Also, if you want to use any of the Dask APIs we talked about, like futures or Dask array or Dask data frame, you might want to look here again at the Dask documentation. Well, there's examples and documentation on all those things. So thank you all so much for your time. I hope this was useful for you.